All right, you guys, chapter 13 um, is a short chapter. It's a nice way to wrap up our course, and we're going to make very powerful use of StatCrunch as well. It's called one-way analysis of variance. Analysis of variance is often abbreviated or spoken simply as Anova. So we learned one type of Anova here, the one-way. There is a two-way analysis of variance. There might be others as well, but I at least know there's a two-way ANOVA. So what's this all about? One-way analysis of variance is a method to test equality of three or more population means. Okay, so you see this is a method to test. This is going to be a hypothesis test, the last style hypothesis test we learned in our course. The hypothesis test makes one last stand here with one-way ANOVA, and we're going to be able to tackle questions that are, of course, different than the ones that we've seen before. These are pretty cool. We're going to look at the equality of three or more population means. So, if we'll have multiple populations, and we'll see, hey, are they all averaging the same, right? And obviously, they'll be closely related. So I've got a couple of examples here. Show you what I'm talking about. Are all approaches to lower blood pressure the same? Medication, exercise, and diet. If somebody's blood pressure went down on one of these three programs, could they expect about the same result? Or maybe one of them is different than the others. And the second one, do four different Disneyland rides have on average the same wait time at 10 a.m.? Okay, so we'll do a practice problem for each one of these. But a couple more details. First, the test is based upon analyzing sample variances. Also, data is categorized by one factor. So there is one characteristic used to separate the sample data into categories. So, we want to see. To do these tests, they take advantage of sample variances. So obviously the sample means themselves are important, but then, how much spread is there? How much might data deviate from that average is critical in our analysis and in our test. And then, of course, it says data is categorized by one factor, and that's where we get the one-way ANOVA. And, we think about the Disneyland rides. Well, there are these four different rides that we'll look at, but they're all categorized by one factor, and that is, what is the wait time at 10 a.m.? Okay. Or for the blood pressure, the one factor that's differentiating them is, are we using medication, exercise, or diet? Right. Okay. These things will be kind of clear once you see it in context. There's also these 5 requirements of a one-way ANOVA hypothesis test. Again, some of these, it seems like a lot, like, wow, 5 requirements. But once we actually see the test, some of them will be, pretty obvious that would have to be the case. I think a lot of these are presented just to distinguish the one-way test from the two-way test. But okay, we'll read them. Of course, number 1, the first requirement for a one-way ANOVA. The populations have distributions that are approximately normal. So each one of your distributions, if you were to think of each category, each one of those would be approximately normal. It would fit a bell curve, more or less. Approximately is pretty loose, by the way. Number 2, each of the populations have approximately the same variance and or standard deviation. So not only do they all fit a bell curve, but they all fit approximately the same bell curve, because they would have the same variance and the same standard deviation. And we're going to assume that the population means are about the same as well. So they're centered at the same spot, and they have the same variance, which is the same as to say the same standard deviation. So not only do they fit a bell curve, but all of the populations we look at fit approximately the same bell curve, approximately. Number 3, the samples come from simple random samples of quantitative data. We can only do this with quantitative data, and nothing fancy about how we take samples. just simple random samples. Okay. Number 4, the samples are independent of each other. So we're not doing any sort of a matched pairs type of sampling. Each population gets its own independent random sample. There's in no way any connection between the two. Number 5, the samples are from populations that are categorized in only one way. So these are one variable, if you will, sort of tests and sort of gathering of data. Again, everything is basically as simple as possible, right? A simple random sample, they're independent, and we're categorizing things only in one way. We're hopefully not saying, we don't want to confuse when we say all these requirements, because when we actually get to the test, you're like, okay, it's just the simplest thing we can possibly do. Okay, so how do we go about this test? So let's talk about the null and alternative hypotheses, and let's talk about the test statistic. Okay, so in the test, we're going to assume that all of the population means are equal. So that's always going to be our assumption. We assume the means for each of the different categories are the same. So obviously, the alternative hypothesis, and we'll see it when we get to practice problem, the alternative hypothesis is going to be that at least one of the means is different than the rest. So we assume they're all equal, and the test is trying to figure out, is at least one of these different from the others? Okay. So, all right, if that's the null and alternative hypotheses, then what about the test statistic? Okay, so the test statistic for an Anova type of test is known as F. It turns out that an Anova test, we need a brand new distribution called the F distribution. Okay, so we call the test statistic by capital F. It is thought of in the following way. Let's take a look. This formula, F equals MS between over MS within. So what is this all about? MS stands for the mean square value. Okay, so the mean square, don't focus so much on what is the mean square. Just think of it like this. MS between is finding the mean square between all of the groups, or between all of the categories. Okay, so whatever that means, it's doing it through all of your different categories, however many there are. Okay, MS within is finding the mean square within each individual category. Okay, so the MS between, what's the mean square between all of the categories? MS within, what's the mean square within each individual category? Okay, here's the thing. Here's why this is going to work. If our assumption is true, if all of the population means really are equal, then the MS between and the MS within should be equal as well. It shouldn't matter if we do it between all of the groups versus doing it in each individual group. If the means are really the same, those numbers should come out exactly equal. Okay, so the idea is if MS between and MS within should be equal, well then if we divide them, we should get 1, right? And you see that in the description. So if the population means are approximately equal, then F will be close to 1. So what does that do for us? Well, if those population means are not actually equal, then we're going to get something different than 1. The further from 1 F becomes, the more likely it is that at least one population mean is different from the rest. So if F is near to 1, then we're probably not going to have enough evidence that one of the means is different. But the further F gets away from 1, the more evidence we have to reject the null hypothesis. Okay. So you're thinking, okay, I guess that sounds fine, but what is the mean square? How do you find MS between and MS within? Okay, that's kind of where we go next. In general, these two values are found by, and we see these formulas broken down a little bit further. MS between, the mean square between, is the sum of squares between divided by k minus 1. Okay, k is the number of groups. So, you might have 3 groups or 4 groups, right? The different categories. The sum of the squares between. So you're finding the sum of the squares between all of the groups. Okay. MS within, the mean square within each individual group, is the sum of the squares within, SS within, divided by capital N minus K. Well, again, K is the number of groups. Capital N is the total number of samples throughout all of the groups. So don't think of the sample size of any one individual group. Think of all of the samples if you put all the groups together. Okay. Now, as we're talking about MS between and MS within, and we see it involves SS between and SS within, and it involves K and capital N, right? Things are getting a little bit more hairy. So kind of the natural next question would be, well, how do we find SS between and SS within? I mean, we could find the capital N and the K, but what about SS between and SS within? So it turns out those are pretty hairy. Not that they would be beyond us to compute, but they would take quite a bit of time, and the chances to make a small mistake are really, really set against us. The chances are very high to make a small error. If you guys would like to know more about calculating SS between or SS within, the sum of the squares between the groups or within each individual group, we can talk about that. And again, it's not outside of our ability level to do that here. It involves a lot of variances. It involves the variances of each individual group. It involves the sample means of each individual group. We can do it, but yeah, it's quite a bit of number crunching, and like I said, the chances to make a small mistake somewhere pretty high. So what are we going to do instead? Well, like statisticians who really work out in the field, they don't do this stuff by hand. Okay, we could do like another rite of passage here for the one-way Anova and do it by hand, and then kind of say, okay, now you learned it by hand, let's do it in StatCrunch. In this case, just by the nature of those formulas, we're just going to do this whole thing in StatCrunch. Okay, so I've got it kind of there at the bottom. However, it turns out that computing SS between and SS within are complicated, and so are typically performed using a statistics software program, and we've been using one of those. Of course, we're going to use StatCrunch to do the work for us. Turns out not only are we going to use StatCrunch to find SS between and SS within, StatCrunch is just going to find that F value for us. It's just going to do the whole thing. There's no way to kind of piece it. We're going to see the data for the SS. We're even going to see the values of MS between and MS within, but at the same time, it's going to tell us what the F value is as well, and we're just going to be able to get right to it by entering in the data. Okay, up next, we've got kind of the background here of Anova. We're going to do the practice problems in the next video.